verified functional algorithms, and then on Friday I'll tell you about something else. And I hope to keep it short and simple. The homework should be easy. Maybe I'll finish my lecture before the end of my lecture time to give you time to work on my homework problems. So let's go. You should write your software in an expressive language with a clean and tractable proof theory, and then prove it correct. And I suggest the language Galena, which is the pure functional programming language inside Coq's logic. And its proof theory is Coq's logic, the calculus of inductive constructions, and then you can prove it correct in Coq. But you should also be good software engineers. You should write efficient programs. So that is, you should use high-performance data structures in these pure functional programs. And since Coq and Galena is a pure functional language, we want data structures that are suitable for efficient programming as pure functional algorithms. So examples of programs written this way are, for example, the CompCert verified optimizing C compiler. Sometimes we need C programs, but compilers never need to be C programs. If what you're doing is manipulating representations of computable functions, you should do that in a language with inductive data types and binders and so on, and so functional languages are good for that. And another example is a static analyzer that we wrote a few years ago in my group, very small, which is a shape analyzer for C programs. And it has embedded within it a resolution theorem prover for entailments and separation logic. And it's all written as a functional program in Galena with efficient functional data structures. OK. And you recall Xavier Loise's claim from last week. Claim, purely functional programming is the shortest path to writing and proving a program. And that's especially true for programs that don't do a lot of reaction with the outside world, with latency requirements. This isn't necessarily the way you would want to write an operating system kernel. But for writing a compiler, yes, it's great. So let's talk about what data structures are in CompCert that make it have adequate performance. And remember, the performance of CompCert is the code it generates is quite good. It's comparable to GCC at the -01 optimization level, which is quite good, but not as great as -02. And how fast does CompCert run itself to compile a program? Well, 2 or 3 times slower than GCC, which is quite adequate because it has fewer bugs. So what are the important data structures that we would have used in the 20th century? Well, fixed precision 2's complement binary integers. Who's ever heard of that data structure? Who's ever used that data structure? Who's ever had overflow in that data structure that led to program bugs? OK, so this is a very important data structure for 20th century imperative programming. Here's another one, the indexable array. Who's ever used that data structure? OK, and very important, it has constant time lookup. If you know the index that you're looking up, you can get to it in constant time. It has constant time update. This is great. Random access. OK, here's another one, the hash table with external chaining. Who learned about this in undergrad? Everybody. Who's ever implemented one of these? Everybody. It's a great 20th century data structure. And these have good performance times. A fixed num, a fixed precision 2's complement binary integer, you can create it in constant time, because that's the machine model. It says so, constant time. You can copy one in constant time. You can add them. You can compare them. And what happens when you overflow? Sad face. OK, you can still deal with that, but it's a pain. And what about the array? You can create it in linear time. That's still pretty good. You can copy them in linear time. That's pretty good. You can look things up in constant time. You can update in constant time. And what happens if you're out of bounds? Well, in some programming languages, it's very bad, because silently the world ends, but you didn't know it. OK? And in other languages, you get an exception. Well, that's better. The world didn't end. Your program ended. But that's not so happy either. With a hash table, again, create and copy our linear time, look up and update our constant time, and when out of bounds, well, that's not really an issue, right? Because it doesn't come up. You hash something, and by the nature of the hash function, you're automatically in bounds. So these are fine data structures with only limited kinds of issues. But, oh, and let's talk about how you prove programs correct. So here's your 20th century proof theory for imperative programming, for logic. You have a precondition P, a command C, and a postcondition Q. And what it means is if your program state satisfies precondition P, then it is safe to run the command C. And then, depending on which flavor of for logic you have, when C terminates, or if C terminates, then the resulting state will satisfy Q. So this is fine. Let's see. X greater than y. X gets x plus 2. X greater than y. This seems good enough as a precondition and postcondition for a command, but not in the theory of fixed precision two's complement integers, because what about overflow? So there's some odd corners there. And here's in the theory of arrays, if a sub I is greater than a sub j, which is greater than 0, and you set a sub I to 0, then the postcondition a sub I is less than a sub j should certainly hold. Who believes that? Come on, raise your hand. Who doesn't believe that? Who has a concrete reason for not believing it? Okay, well, let me give you a concrete reason. What if I equals j? Now think about that. This is the aliasing problem for updatable data structures, and it leads to problems in program verification. Yes?
If a sub I is greater than a sub j, I can...
Oh, yeah, you've got a point there. So I should have put a greater and or equal in the right place. All right, but this is a good point. Okay, so whatever. So here's our choices in the formal verification of correctness of software. Choice 1, we could fix up the proof theory of imperative programming to account for all the corner cases and to deal with pointer data structures and aliasing and all those other things. And actually, that's what I'll talk about on Friday with my lecture on the verified software toolchain. And a different presentation of that was made this morning by Zhang Xiao, who talked about verifying C programs in a quite different way, with a different approach to proving things about imperative programs. Choice 2 is program in a style that supports a simpler and cleaner proof theory, that is functional programming Galena, verified in the calculus of inductive constructions. So that's what I'll talk about today and tomorrow and Wednesday. And we will not be using fixed nums, not because you couldn't do fixed nums in a functional program, but because in the 21st century, we don't want to deal with issues about incorrectness of programs when they overflow. We needed to do that in the 20th century. Memory was expensive in the 20th century, right? But in the 21st century, by and large, for most applications, we can tolerate representations of integers that are tolerant of big values. So here's one, nat, right? It has 0 and it has successor of n, and it can't overflow. Yeah, eventually you'll fill up memory, but you're not going to have wrong values because you wrapped around or something. The problem with nat is that operations on nat can take time proportional to the value of the number you're operating on, and that's a very high performance penalty. So there's a data type in Coq, built into the Coq library, called positive. I'll get there in a second. But let's talk about the costs. Creating a fixed num, or creating a nat takes constant time. That's good. Copying a nat takes constant time. Even if your nat is 1,000,000, so it's occupying 1,000,000 chained links of memory, to copy it, you just have to copy the head pointer. You don't need to copy in depth because these are functional programs. So nobody's going to modify one and let somebody view the other because there's no update. So this is a good thing. Constant time copy. Adding can take time O of n, where n is not the sort of size in conventions of computational complexity theory where it's the value of the number. And compare takes time proportional, worst case, to the values of the numbers. And those are very bad. And then we don't have a problem with overflow. So let's talk about positive numbers. what we're going to do is take the binary representation of the number and encode that as an inductive data type. So here we have inductive positive with 3 constructors. XH means the number 1. And XO means, XO of n means 2 times n. And xi of n means 2 times n plus 1. So each XO digit is like a binary 0 digit, and each XI is like a binary 1 digit. And when I say means, well, a Coq inductive data type doesn't mean anything. It's just syntax. So we give it some interpretation, and we write our programs according to that interpretation. And then if our programs end up somehow semantically respecting that interpretation in some way, then we get to say, yes, it turns out it did mean that. So 13 is encoded as, let's see, xi of xo of xi of xh. Right, so this one right here. There's also notation for it with this tilde. So p tilde 1 is notation for xi of p. The tilde notation you won't need much. The notation we want for this funny thing is 13. Okay, and we don't really want to program much with these xi's and xo's. We just want it to be reasonably efficient. And now how efficient is positive? Well, creating them takes constant time, and copying them takes constant time for the same reason that copying nats took constant time. We just make a new pointer to the existing number. And adding them takes time log n, where n is the value we're adding. And because, well, the whole length of the number is n, and even if you need a recursive function that walks down 2 numbers bit by bit, adding them up, which is what happens, it's log n time. And compare takes log n, and they can't overflow. And these really can't overflow, because by the time one of these fills up memory, you're representing quite a large number. Okay, so you might want positive and negative integers, and 0 even, right? We should catch up with the invention of 0 3,000 years ago. So here's the inductive data type that's built into the Coq library called Z to represent the mathematical integers. It has 3 constructors, Z0 representing 0, ZPOS, which takes a positive number. ZPOS of n represents as an integer the positive number n, and Z negative n represents the opposite of that. So 13 as a Z is represented this way, ZPOS of all this stuff. Okay, so again, create and copy take constant time. Add and compare take log n time. They don't overflow. This is a very nice representation. Now, you could be proving things in Coq about integers for quite a long time and not actually know that that's what's going on under the hood. Raise your hand if you're in that situation, or at least raise your hand if you're in that situation now, or you were for at least a year at some point. Okay? That's great. That's what data abstraction gives us. And yet, the operations on these things are efficient enough. Well, is this efficient enough? Log n versus constant time. And the space cost, of 13 is 1, 2, 3, 4, 5, 6, 7, 8 words of memory compared to like 1 in the fixed precision. Yes, the entire CompCert verified optimizing C compiler is programmed this way. It uses positive numbers everywhere to represent identifiers that it looks up in tables, right? There's no special trick in the extraction of CompCert to use more efficient data types than the plain old Z and positive that I've shown you already. And it runs fast enough, all right? So here we have a log n cost factor. The log n cost factor may come from the fact that we're doing purely functional programming, or it may come from the fact that we're tolerating, overflow or something. And we are willing to tolerate a log n cost factor. Yes?
When CompCert gets extracted into OCaml, doesn't you end up using OCaml integers
When COMSIRT gets extracted into OCaml, doesn't it end up using OCaml integers? No. Okay. Okay, so, but it runs fast enough. And it doesn't have bugs caused by using OCaml integers that might have overflowed. Right? If we want to prove the thing is correct, we have to resist sometimes the temptation. So I will talk about use of OCaml integers in my lecture on tomorrow, so just wait till I get there. Okay, so these are important data structures in 21st century functional programming. Let me show you another data structure, list of Z. 3 cons 4 cons 1 cons 5 cons 9 cons nil. So there we are. It's a list. This would have been recognizable in 1960 when this data structure was invented as part of the Lisp programming language. And remember, each of these numbers is really a pointer to one of these guys. That's a very important functional data structure for the last 57 years. Okay. Now let's talk about the cost models for programming this way. If we're writing efficient programs, we need a mental model of how much time things take and how much space they use. So here's a function, cons twice. Cons twice takes x and y, and cons is x twice onto the front of y. And what does it cost? Well, here's an x. Here's a y, and remember that each of these numbers is one of those things as well. And we run cons twice, and look, it creates 2 cons cells, right? And this is the result it returns. It does not copy the rest of the list. So the first thing to remember is that no matter how big y is, this has cost 2 cons cells, right, in terms of time. To create 2 cons cells, you have to store 4 words to initialize them. That's what it should cost to create 2 cons cells. And indeed, it doesn't cost much more than that. And then you might have to garbage collect those cons cells eventually. That costs less than the 4 words of storing that it costs to initialize, right? That's the time cost. Now, what's the space cost for consing? So here's a little function. Swap first 2 takes a list. If the list has at least 2 elements, it returns the list with those 2 elements swapped. Otherwise, it returns the original list. And here, let p colon equal 1 cons 5 cons 9 cons nil in swap first 2 of p. So that does this. It creates p and then creates the swap first 2 of p. And then what's the cost, the space cost, of doing that operation right there, y cons x cons BL? Well, 2 cons cells are created, the red ones. 2 cons cells become garbage. They are now inaccessible. The garbage collector will collect them. So the net cost, the space cost of that line, is 0. And in general, when you measure the space cost of running a function, you need to know, in the context that that function is run, is somebody holding on to the old values of some data structures or not? Because that will determine whether the garbage collector is reclaiming certain cells within the data structure. So these are important principles for reasoning about the time and space costs of your functional programs in strict functional programming languages. They are 20th century principles. Zhang Xiao and I wrote papers about them in the 90s. And that's how you should think about your Galena programs as well. So Galena, you will tend to extract to some other programming language, such as ML or Haskell or whatever, and compile with your ML compiler or Haskell compiler. And so you're really modeling in your mind the time and space costs of running those programs as extracted. So for the rest of these lectures, I will assume that you're extracting to ML, that is to say, a strict functional programming language. Now, there was a question?
Why do you not have a reason about who's holding on to, like, aliases of P, for instance, or Q, for instance?
Here, nobody's holding on to aliases of P because it's a local variable. And nobody's holding on to aliases of Q because I just created Q.
Gotcha. Sorry.
Okay. Okay. So, right. So here's the plan. We will implement algorithms that are correct and efficient. We will use Coq to build machine-checked proofs of correctness. We will not do machine-checked proofs of efficiency. It will just be true that they are efficient for reasons we can explain, which in the 20th century was called a proof. Okay? And sometimes formal machine-checked proofs about the properties of data structures will help in the proofs of efficiency. If I have a tree and I can prove that its height is bounded by log n or 2 log n, and then I do informal, and that's a machine-checked proof, that can still be useful in my informal reasoning that this algorithm takes time proportional to the height of the tree. Okay, and that will guarantee with very high assurance that the programs give the right answer, and with less high assurance that they run fast enough. But you know, the user can see if they run fast enough. What the user is not sure of is the answer correct? Now, that's not always true. Sometimes it would be, sometimes you need to know that tomorrow it will run fast enough, but it's just beyond the scope of what I'm doing here. All right, so here's the outline. In today's lecture, I will tell you about simple sorting algorithms, and mainly to set you up for doing homework about simple sorting algorithms. Tomorrow, I'll talk about search trees, and Wednesday, or maybe starting tomorrow, I'll also talk about balanced trees. And then on Friday, I'll talk about verifying imperative programs with verifiable C and separation logic. Okay, so here's a sorting algorithm. Insertion sort. Who has ever programmed up an insertion sort? Who has ever programmed up an insertion sort in a functional programming language? All right, good. So this will not be news to you. The green part is the stuff that's already sorted. The white part is the next thing we're trying to insert into the sorted list. The purple part we haven't looked at yet. We're going to insert R into the sorted list F. Now we're going to insert I into the sorted list FR, so it goes in there. Now we're going to insert B in the sorted list FIR, so it goes in there. And in each line, we have to sort of move this back up to, well, if we're in the ith position, we have to move this back up to I times. So the cost of sorting the whole list is, at worst, I plus, at worst, 1 plus 2 plus 3 plus 4 plus 5, the triangular number of n, or order n squared. So you knew all this. And here's selection sort. Pick the smallest element and put it at the front. So there's the smallest element, put it at the front. Now, in the remainder of the list, pick the smallest element, put it at the front of the remainder of the list, anyway. And now pick the smallest element of the remainder of the list, put it at the front of the remainder of the list, and so on. Okay, who has seen that algorithm before? Yes, good. I told you this was going to be easy. And sometimes you want data structures that aren't quadratic time. So here's binary search trees. You want a lookup table for looking up keys. Let's say out of this set of keys, FRIBBLE. So we insert F in the binary search tree. Who has seen binary search trees with insertion and lookup before? Good. So I'll just whip through this. This is what happens when you insert in a binary search tree. And, all the keys to the left of this node are less than F. And all the keys to the right of this node are greater than F. And that property is true sort of recursively. All the keys to the left of this node are less than R in alphabetical order. So I and L are both less than R, and so on. So in the average case, or if you're lucky, the height of this tree is log n. And in the worst case, if you insert in an unbalanced way, the height is n. So how could you get unlucky? If I put the B in first, and then the E, it'll go off to the right, and then I put the I, and that goes to the right of the E, and I could keep putting in nodes to get a maximally unbalanced tree whose height is n. And then looking something up in that really unbalanced tree would take linear time. Let's say n over 2 on the average. So in the average, that doesn't happen. The average case of this tree is log n, and that's a good thing. And the worst case hardly ever happens. Ha, ha, ha. OK, but just in case you want to be sure, you can make your trees be better balanced. So here's the notion of a rotation in a binary search tree. L is greater than I. We could rearrange those two nodes with the I and the L so that the L is on top and the I is its left child. So it looks like that. The three subtrees, G, J, and M, are still there untouched, just where they were, but now the two nodes I and L point at them in a slightly different way. So that was a left rotation. We could do a right rotation here with L and R. So let's do that. And now we have reduced the height of this tree, because the three nodes I, L, and R, which used to be sort of chained in height 3, are now balanced in height 2. So the principles of balanced binary search trees is that these rotations in your trees can be done to reduce their height. And generally, you keep the height of the tree to be no more than 2 log n. OK, so that's balanced binary search trees. And in red, I've indicated the depth of each leaf. So you can see the depths of the leaves vary from, but the deepest leaf is no more than twice as deep as the shallowest leaf. So we call this balanced. And therefore, the height of the tree is no more than 2 log n, and therefore the maximum search time is no more than 2 log n. OK, so what are the operations on balanced binary search trees? Well, create an empty tree, let's say. Insert a node into it, or insert a key binding pair into a binary search tree. Because typically you don't just have keys. You can use binary search trees to implement finite maps, mapping some totally ordered type, your key type, to some other value type, which has no particular constraints on it. And that implements a finite map from keys to values. And so insert takes a tree and a key and a binding and inserts that key binding pair in the tree, replacing the old key binding pair for that key if there was one. And then lookup takes a tree and a key and tells you what binding, if any, was there. Those are the core operations, but here are some more operations that are useful. Take the union of the key binding pairs of two binary trees. Or if the same key is present in both trees, let one tree have priority. So union, intersection, convert a binary search tree to a list of its key binding pairs in sorted order by key. That's useful. Or if I have a list of pairs in sorted order by key, convert it back to a binary search tree. Or find and remove the minimum element from a binary search tree. Now, if you can do all these operations, what do you get? Well, delete min is useful for using binary search trees as priority queues. Union and intersection are useful for using binary trees to manipulate sets of free and bound variables, right? Think of 2 or 3 of the lecturers last week. Stephanie Wyrick, Xavier Lois, who else I can't even think of, who were always doing unions and intersections of sets of variables. Well, if you have a compiler or a static analyzer or some other analyzer of programs, there's hundreds of variables in programs. The ones that fit on their slides did not have hundreds of variables, but real programs have hundreds or thousands of variables, and you need to do these kinds of operations on them efficiently. And you can use binary search trees and balanced binary search trees to do them in pure functional programs pretty easily. It is not the case that union can be done in log time. It might take n log n or whatever, but still you can get pretty efficient programs. OK, so that's the end of the slideshow. It's time to do some programming and proving in Calc But I'll stop here for questions about the slides. No questions. All right. Yes.
Where are these checked in?
I will check them in. Yes.
So one question about these efficient data structures for numbers. Do you also have some efficient way of dealing with the fact that you sometimes need to use natural numbers as fuel in your functions in Coq? Because you may want to translate from these efficient representations to a net number to use them as fuel.
Okay, so the question is about the use of natural numbers as fuel. There's several ways to approach that. Okay, one way is to use positive numbers as fuel, and then you can't use the fixed point of Coq. You must use the function with the measure that's the positive number. That's very straightforward, but tedious. Another way is to, if you know that the fuel you're going to use is proportional in size to the actual number of iterations rather than just some extreme upper bound on the number of iterations, go ahead and use the natural numbers as fuel. That's a little less than satisfactory. The third approach is don't use fuel. Use the function mechanism or the program fixed point mechanism that doesn't need fuel. You know, if you read Adam's book, CPDT, there's a chapter that describes 4 unsatisfactory ways of dealing with recursive functions. But, you know, 4 unsatisfactory ways is better than no ways at all. Fuel is just one of the unsatisfactory ways. So that's one kind of answer. Other questions? I'm just not so interested in machine-checked proofs about the asymptotic complexity of programs. I need the programs to compute the right answer.
So there's nothing fundamentally hard about it?
Oh, well, I don't know if there is. I mean, one thing really beautiful about Coq is that it has a programming language with a proof theory that are all integrated and work well. And when you have to tack on a separate proof theory for reasoning about something about your program, is it as beautiful? Often not. So I'm just not going to go there. Yes?
So you advocate using Galena to write programs that you want to verify. So that's what if you want to extract them, but what if you want to compile them? Once you've verified that they're correct, you want to compile them, then how would you go about reasoning about Galena programs inside Coq?
I'm not sure I understand the question.
So if you write the program in Coq and then extract to OCaml, that's very well. You prove it's correct, you can use it in OCaml. But what if you want to write a compiler in Coq from Galena? I mean, if you want to compile this program that you wrote in Coq and still preserve the correctness, then you're going to have to reason about Galena programs inside Galena, inside Coq.
Well,
I think you're talking about adding a layer of reified syntax.
Yeah, well,
I think whatever the question is, the answer is Coq.
well, okay. So if, you know, the Galena functions that I'm going to write here are not at a level of reified syntax. They are just written down inside Coq itself. And there's, in the logic at least, there's no particular level of sort of reification or syntax. It's just Galena integrated and reasoned about in its own logic. That's the only way I know of to answer the question. I don't think the answer is Coq, which is, Coq is a great answer to lots of other questions, but maybe not that one. Yes?
All we're talking about here is asymptotic complexity, but this is not what algorithms people care about, right? They also care about the constant.
Okay, so I have done the following thing when it's necessary. Write a functional program in Galena, compile it with, extract it and compile it with OCaml, run gprof. Who here has ever run gprof? Okay, run gprof to measure the hotspots, figure out which algorithmic tweaks and data structure representation improvements are necessary, do those in the Galena function, and repeat. And you can read about this in a paper by Stewart, Beringer, and Appel called, I think, Veristar, which describes this process of algorithmic tweaking by running the profiler on the lowest level program. So yes, you do that. It's called engineering. We are engineers here. Okay, so I'm going to be talking about sorting algorithms today. And before we talk about sorting algorithms, we have to talk about what the sorting algorithms do. They rearrange the elements in a list so that they are increasing order, right? So it's easy to, if I ask you what should the specification of a sorting algorithm be, you might respond, well, the resulting list is in non-decreasing order. And some people forget to say, and the resulting list is a permutation of the input list. Because otherwise, it's really easy to write sorting algorithms. Return nil. OK. So we could say we need to reason about permutations in order to prove things about sorting algorithms. That's not quite true. There's an alternative formulation of the correctness of sorting algorithms based on these two lists should represent the same multiset of elements. Right? So now we talk about multisets, mapping of keys to multiplicities. And we can do it without permutations. But here, I will do it with permutations. OK, so in this file, perm.v, so the first step of the homework is to grab the VFA from the distribution for this summer school and type make in that directory and open up perm.v in your favorite interactive development environment for Coq, which probably isn't Coq IDE, but what the hell, that's fine, I don't care. And follow along later on with what I'm telling you now.
What's subdirectory?
VFA should be. What?
In the DSSS17 repo, go to the SF directory and then the VFA subdirectory.
Right, DSS, okay, 17/SF/VFA. All right, now, before we do permutations, let's talk about comparisons of perm.v. Okay, permutations. But before permutations, let's talk about comparisons. And as you've seen already in the Software Foundations bootcamp, there are comparisons on natural numbers. Here I'll just use natural numbers in this lecture, even though they're inefficient. But there's comparisons on natural numbers that are propositions. A is less than B. And there are comparisons on natural numbers that are functional programs that return a Boolean. And we distinguish those two things in this logic, the calculus of inductive constructions. We have to distinguish things we compute from mathematical propositions because, I don't know, because otherwise the logic doesn't work so well. And that means we have two kinds of, we have nat.lt, so the less than comparison operator. Yes, question? I could make things bigger, or you could move closer to the front. There's lots of seats down here.
Yeah, more.
One more.
Can you sort the audience by side?
Okay.
More.
More?
Maybe from the front. Yes, thank you.
All right. Let's see if we can do it this way. All right. In the Coq.
More would be great.
Yeah, like twice.
Some of you who are sitting way in the back, so I won't call on you, could move down to the front for the next lecture. But for now, I'll make it even bigger. Okay. So,
But by the way, I will just note that now I can read it in the front.
all right, fine. We have LT from nat to prop. That's the propositional test for less than on natural numbers. And it comes out of the part of the Coq standard library from module nat. And the module nat has been opened by a kind of import, right, as part of, I don't know, importing and re-exporting this coq.arith.arith. So LT is actually the same thing as nat.lt. And here's how you can tell they're the same thing. You assert it and prove it with reflexivity. There, it's the same thing. Now, we have nat.ltb, which is less than returning a Boolean, which has type nat arrow bool. And then there's notation, right? The less than symbol. So if I locate underscore less than underscore in quotes, and by the way, if you're trying to figure out what notation means, you should use locate with quotes like that. It's very handy. And I don't even think you need the underscores. It's just that if you don't put it the way I did with the underscores and the spaces, it gives you every notation that uses a less than in any kind of way, which is also handy. All right, so what we find is that the less than symbols is notation for the LT operator, and that the less than question mark symbol is notation for the Boolean test that's a computational algorithm. And if you recall from the boot camp or from your own introduction in software foundations in the past, LTB is a recursive function that walks down natural numbers until it comes to the end of one of them or the other. Okay, it's a computation. Okay, and we have here LTB-LT, which is a theorem, a lemma. It's not fancy enough to be distinguished with the name of theorem. Okay, and it says if the Boolean test on n and m returns true, if and only if, then n is actually less than m. So when we do proofs about programs, in proof land we want to be thinking about propositions, but in program land we have to use these Boolean tests, and it can be a pain to get between one and the other. So let's see some way right here to minimize that pain. And there are several different approaches to this, and this is not the only one that works, but here's one that works. So relating prop to bool. Let's look at reflect. Reflect is an inductive data type in the Coq standard library. And here's what it does. Reflect of P, where P is a proposition, takes a Boolean and returns a type, a set, whatever. And it has two constructors, reflect T and reflect F, suggestively named. Reflect T takes a proof of P and returns reflect P true. And reflect F takes a proof of not P and returns reflect P false. So if you have a proposition that's true with a capital T, reflect relates it to true with a small t. And if you have a proposition that's false with a capital T, then reflect F relates it to false with a small f. And if your proposition is neither true nor false, then I guess reflect can't help you. Okay, now, here's a theorem. It's called BEQ reflect, and it says, reflect, for any x and y that are natural numbers, reflect relates x equal y with x equal question y. Equal question is EQB. It's that Boolean test, that Boolean function that walks down natural numbers to see if they end at the same time. Okay? Yes?
So this is the second time in 2 weeks that we see this lemma in the slides. I'm confused. Are these being included every time for didactic reasons, or is the working programmer expected to improve BEQ reflect in all their developments separately and fresh?
The working Coq developer is expected to manage libraries in some sane way, and sometimes the Coq standard libraries help with that, and sometimes they don't. Okay, so let's prove this thing. We can apply a theorem called if and only if reflect, and then this is what we have to prove. The internals of this theorem are not so interesting. Let's just say that there's these three theorems that are easy to prove, and they work like this. BLE reflect proves that x less than or equal to y relates to x less than or equal question mark y, which is the Boolean function to calculate it. And BLT reflect relates the proposition x less than y to the Boolean calculation x less than question mark y. Okay, and now let's do an example. We want to prove this thing. If a less than question 5, then a else 2 is less than 6. So this computation tests a against 5 and then returns either a or 2. And we're going to destruct, we could destruct a less than question mark 5. That's not going to work. We destructed this a less than question mark 5, but forgot to remember, what it was while we destructed it. So we could do this. Destruct it and give me an equation about it. That's better. At least this goal is provable, but it's sort of painful to prove. Who's ever had to prove painful goals like that? Yes, I know you're out there. So instead, we will destruct this inductive proposition, BLT reflect A5, which BLT reflect A5 is an inductive proposition from an inductive proposition type with 2 constructors. So when we destruct it, we will get 2 possibilities, and let's call each of them H. And the first possibility is that H is less than 5. Where did that come from? Remember, reflect takes a proposition P, right, and then a proof of P, and relates it to true. So H is the proof of P that had to be embedded in that reflect thing. And there it is. From H equals 5, from a less than 5, we could prove a less than 6, which I will use the omega tactic for. I'll talk a little more later about omega, but it's handy for proving these things in linear arithmetic. In the other case, we have not a less than 5. Okay, and we could use omega directly here, or if you like, we could first apply not less than in H and get a greater than or equal to 5. But in any case, 2 is less than 6. Okay, so in the theory of linear integer arithmetic, 2 is less than 6. Okay, I made this fancy tactic using proof automation, and I'm not going to explain to you the workings of the tactic, and you don't need to know how it works, but you're free to experiment with it and sort of see if you can figure out what it's doing by looking up some of these things in Chapter 9 of the Koch Reference Manual, which explains the tactic language. We want to prove if a less than question 5, then a else 2 is less than 6. So I will say B destruct, Boolean destruct, a less than question 5. So here we go. All that does is a destruct of the reflect that I did in the previous proof. But I don't have to say destruct or reflect. I can just say the Boolean test that I was interested in is this one. Do a B destruct, do a destruct on the reflect of it. And now we get nice propositions above the line, not Boolean tests. And the rest of the proof is the same. We can just use omega. And this one, the other case of the B destruct is a greater than or equal to 5. So that's a nice propositional fact about arithmetic. Okay, so that was Booleans. Here's one of my favorite tactics. It's about inversion. When I do inversion H, Koch is supposed to extract some true things from the thing I inverted and put them above the line for me. Well, Koch is so good at extracting true things out of H that it always extracts enough true things that if you had those, you wouldn't need H anymore. Koch's inversion is never so stupid as to leave things inside H that it didn't, tell you in extra equations below the line. Yes?
So what you said is not technically true, but it takes a lot of explanation to explain why. Just thought I'd add that.
The question was, what I said was practically true, so he won't talk about it anymore. Okay, so one of my favorite tactics is this one, defined in LTAC. inv of h is inversion h, clear h. You don't need it anymore. Everything inversion was going to learn is practically there for you. And then substitute all of the equalities it gave you. So I'll use that a lot. Okay, now let me talk about linear integer inequalities. I want to prove this stupid lemma. If I is less than j and not of k minus 3 less than or equal to j, then k is greater than I. Is that true? Let's see. So k minus 3 ought to be greater than j, and I is less than j. So k minus 3 should be greater than I. That's sort of believable. I claim to you it's true. I'm not trying to trick you. Who believes it's true? Who believes it's true just because I said so? Okay, well, the rest of you can stare at it until you believe it's true, but it's true. So how do you prove this in Coq? Well, it's so obvious, right? It's the transitivity of that and what is... So here's how I would prove it in Coq if I didn't have a better way. I would say there's got to be some tactic that relates not and less than or equal to greater. But I can't remember its name, right? We weren't built to remember all the names from the Coq Standard Library. So we'll do search about. Search about. Give me the name of some lemma that relates not of something less than or equal to something, implies something else. And it tells me, well, there's not less than or equal, which says not of n less than or equal to m, implies n greater than m, and that's the one I want. Yes?
Search about is differentiated in code 8.6.
Yes, well, but I'm older than that, so yes. So yes, indeed, you could say search, and it would do the same thing. Okay, so that's the one I want, not LE. So I will apply not LE in H0. Okay, good step. And now, there's got to be some lemma about the transitivity of less than, but I can't remember its name either. So let's search for lemmas that look like they're about the transitivity of greater. And there it is, GT trans. So let's apply GT trans. Okay, now I've got to prove k is greater than j. Well, k minus 3 is greater than j. So let's do GT trans. First we'll prove k minus 3, k is greater than k minus 3, and then k minus 3 is greater than j. But the second, the 2 out of 3, is an assumption, so that's easy. And what about the first one? Obviously, k is greater than k minus 3. Who believes it is? Ha ha ha, you're reading ahead. K is not greater than k minus 3. Because we are talking about the natural numbers with subtraction. And the natural numbers don't have subtraction. What they have is bogus subtraction, right? That 2 minus 3 is 0 in the natural numbers with bogus subtraction. So therefore, this proof goal, k greater than k minus 3, is not true. Okay, so here's a theorem. To prove that k is not always greater than k minus 3, I'll prove the opposite. It is not the case that for all k, k is greater than k minus 3, and I can intro and specialize h with 0. So now I got to prove this, and simple in h, and inversion h there. I proved that bogus subtraction is bogus. Okay, so we could fix that. And we want some other, look right here. I searched for a slightly different transitivity lemma and applied that slightly different transitivity lemma there. And now the rest of the proof goes through. Oh, but that was painful and exhausting. And you know, if proving the correctness of our verified functional algorithms involved proofs like that, whenever you happen to use a less than in your program, we should all just pack up and go home. Okay? So fortunately, it's not like that. Here's my new proof, omega. Okay? So omega is a decision procedure for linear integer arithmetic. That is arithmetic with integers and inequalities, greater, less than, and multiplication by small constants. It's It was invented in the mid-90s by Bill Pugh at the University of Maryland, I believe he was then, and he invented it he had a parallelizing compiler for, Fortran-like programs with arrays and array subscripts. And when you parallelize so that you subscript this element of the array before that one, and you want to switch things around, you have to prove that the array subscript here, whatever expression that is, I times 3 plus j, is not equal to the array subscript here, which is 2i plus 1. Okay? And in order to prove those things, you needed a solver for the theory of linear integer arithmetic. And that algorithm is not the most powerful solver there is for linear integer arithmetic, but it works pretty well. It's easy to use. It's widely used in proof assistance and elsewhere for people that even don't care about parallelizing Fortran programs. Okay, so you use omega. All right, now let's move on to sorting. I have a little proto-sorting algorithm here. So it takes a list AL, and if AL has at least 2 elements, A and B, then it reorders them so that they're in increasing order. So if A is greater than B, then switch them, otherwise don't switch them. So that's maybe swap. Let's try it out. I claim that maybe swap of 1, 2, 3 equals 1, 2, 3. So I could simplify. And yes, it's true. And maybe swap of 3, 2, 1 equals 2, 3, 1. And yes, that's true. Okay. And notice that in the program, I had to write greater than question mark. If I had written greater than, it wouldn't have type checked, because that's a proposition, and you can't put propositions in your if-then-elses like that, in your matches. You can't. All right. So, right. I explained all this already. So here's a theorem. Maybe swap is idempotent, which is to say, if you apply it twice, you get the same result as just applying it once. So let's see how we would prove that. By case analysis, right? Maybe swap is defined by case analysis, so we can destruct AL to see if there are at least 2 elements in the list to see which case of maybe swap is going to apply. So we can destruct AL as either nil or A cons AL. And here's the nil case. So if we simplify, then we've run maybe swap on the nil in 3 times, actually, if you think about it here. And that simplifies down to nil equals nil, which we can prove by reflexivity. Okay, and if we simplify now, well, it's a bunch of pattern matching on AL. Well, 2 of the pattern matchings are on AL. Then there's an if statement, and then there's whatever. Let's destruct AL again. So this AL will destruct as either nil or B cons AL. So now we've got maybe swap on a singleton list, and if we simplify that, we find that it's proving that a list equals itself. So that's fine. So this is the final case, the third case. The list has at least 2 elements. And let's simplify down maybe swap. Doesn't simplify much. So what do we do next? We're going to do more case analysis. Either B is less than A or it's not. Okay? So let's destruct B less than question mark A with equation H. Fine. So we got 2 cases. This is the B less than A equals true case. And if we simplify it, so we had maybe swap applied to that, and we simplify it down, and we get another if statement. But now it's if of A less than B, because this is the second application of maybe swap, so we've already swapped something. So we should destruct that if. All right? So now we've got this case in the case analysis. B less than question mark A equals true, and A less than question mark B equals true. And those are things about tests on Booleans. So omega doesn't do tests on Booleans. If I put the omega here without a try, just to indicate what's really happening, omega can't solve this system. Omega solves things about the less than operator in the propositional part, not in the less than test as a Boolean function. So this didn't do anything. So let's give up and let's do it a different way. Get back to where we were before the destruct on b less than question mark a. And here's how we want to do the destruct on the reflect of BA. Because what that does is what it puts above the line after we do the destruct, look up here, it's the proposition L, standing for less actually, colon, B less than A. All right? And in that case, B less than A, let's simplify this down. We want to do a destruct of BLT reflect of AB, or equivalently, we could say B destruct A less than question mark B. So let's do that. Now we've got two cases in this case, but now above the line we have B less than A and A less than B. And if we plug that into a decision procedure for the theory of linear integer arithmetic, it discovers that that's not solvable. So omega solves that case, and we're done. Even though the thing below the line does not obviously appear to be in the theory of linear integer arithmetic, it's in the theory of lists. But above the line in linear integer arithmetic is a contradiction, so that's good enough for omega to solve this subgoal. This subgoal, below the line, looks very nice. It's just solvable by reflexivity. And now we're in the other case. Above the line, we have not B less than A. If we simplify this, what do we have? We have another B less than question mark A. So let's do a B destruct on this thing right here. Can you see that? Yes. That's the thing we're destructing. And we're going to have two cases. Above the line, there seems to be a contradiction. So omega will notice that contradiction, and that's fine. Here above the line, there's no contradiction, but below the line, there's something obvious. All right. So that's how you prove sorting algorithms. There's not much to it, right? You need to reason about swapping of things, and you need to reason about comparisons. I guess to sort things longer than 2 elements, you might need induction. So, okay, so let's talk about induction. Let's see, is there anything I want to say here? No. Okay, permutations. So if we go here, if I say locate permutation, it says inductive coq.sorting.permutation.permutation. And there's a module called permutation as well. So permutations are there in the Coq standard library. So what is a permutation? If I say check permutation, it says permutation is a thing of type for all A, list A arrow prop. So it's a relation on list of A for any type A. And that makes sense. You permute a list of something to get another list of the same type. Okay, let me print permutation. Okay, and here's what you get. Permutation is an inductive proposition with 4 constructors. That nil is a permutation of nil. That for any x and L prime, if there's a permutation from L to L prime, then there is a permutation from x cons L to x cons L prime. And then perm swap says there's a permutation from x cons y, y cons x cons L to x cons y cons L. And finally, permutations are transitive. If there's a permutation from L to L prime and a permutation from L prime to L double prime, then there's a permutation from L to L double prime. Okay, well, here's the problem. All of these things look true enough. But why should we believe that that captures everything there is to know about permutations, right? That if something's a permutation, it's captured by this inductive presentation. Yes?
Because you can prove that all permutations result down to 2 swaps. So that's a theorem
you can only prove that all permutations result down to 2 swaps if you have a definition of what is a permutation. This is purported to be the definition of what is a permutation, but you know, we're starting by assuming the thing we're trying to prove. So this is a problem. When you prove the correctness of your functional programs, even knowing whether you've got the right specification is an issue. So what can we do about that? Here, well, here's one thing we can do about it. Search about permutation. And what you find is some lemmas and theorems proved in the Coq Standard Library about permutations. And the first 4 of them are the constructors of the data type, so nothing new there. But now we have all these others that if there's a permutation from nil to L, then L equals nil. And it is not the case that nil is a permutation of x cons anything. And permutations are reflexive. L is a permutation of L. And if L is a permutation of L prime, then vice versa. And what? If I have a permutation from L to L prime and x is in L, then x is in L prime. That's handy. Yes?
Technical note, since I've followed along, search works a lot better at 8.6 than search about does in this instance.
Yeah, well, fine. I'll put search, because search about is deprecated. All right. So one way you could become confident that this is the right definition of permutation is that all of these things are true. But maybe that's still not enough, because if lots of things are true about permutations, then I could satisfy that with that any 2 lists are permutations of each other, and then you could carefully check that all these properties are true. And very few of these are negative properties, and you might not notice. So there is a theorem, permutation length, actually, that helps. If L permutes into L prime, then the length of L equals the length of L prime. So that rules out some things as being permutations. All right, so I claim that this is an adequate definition of permutation. It captures the right property, and we can go ahead and use it, and we will go ahead and use it. So there's no trick here. It's just that you should be suspicious. All right. So let's use the theory of permutations in Coq to prove a theorem. And here's my theorem that butter appended with fly permutes to flutter appended with by. Okay? These are both lists of what? I don't know. I have, oh yeah, for all natural numbers, B-U-T-E-R-F-L-Y. So these are lists of natural numbers. Okay, so let's use the Coq theory of permutations to prove that one really is a permutation of the other. And just to illustrate a method of proving things about permutations that may be useful to you in proving things about sorting algorithms, I'm going to change B-U-T-T-E-R to B append U-T-T-E-R. And I use change because these really are beta eta equivalent by unfolding the append plus plus. And so there I have B append U-T-T-E-R append fly. And I'll do the same thing with flutter. I'll change flutter to FL append with utter. So now I have these. And let's remember U-T-T-E-R as utter. Okay. So now this is my theorem. And now it doesn't matter what's inside utter. So I'm going to clear that from the context. I'm going to clear HQ utter. And so that disappears, right? And now this is the theorem I want to prove. Yes? Oh, well. equivalence in calc is, there's no eta eta. You expand out to beta normal, eta long, whatever, yeah. So beta equivalent, but beta delta equivalent, right? And iota and zeta, but not eta. Okay. All right. How do we prove this? Let's see. I'm going to rearrange those appends so they're not parenthesized that way. So I'll rewrite left by append associative, and you can see what that does. It moves the parentheses around the a plus plus b plus plus c to the right. So now I have that, and I'll rewrite again by append assoc. Okay, so now this is what I want to prove. And then next I'm going to use the transitivity of permutation. So if I check perm trans, it tells me what the perm trans lemma does. It proves permutation L prime prime from in 2 steps. So I will apply perm trans with this intermediate thing, utter append fly append b. So I've swapped things around, which seems reasonable enough. I'm doing permutations. So this is my proof goal now. Okay. And I will again rewrite by the associativity of append. Instantiated with utter and fly, so I can tell it which append I'm trying to rewrite with. Okay. Oh, this is getting better and better. So I have b append utter fly is a permutation of utter fly append b. And there's a theorem about the relation between append and permutation. It says the permutation, that L append L prime is a permutation of L prime append L. Somebody had to prove that. It wasn't built into the inductive data type, but it's a theorem in the standard library, and I can just apply it right now because that's the situation I am in. Bingo. So this is the remaining subgoal. So I'm going to apply perm trans. I say there's some intermediate thing, question mark L prime, that this permutes to and that permutes to the other thing. And in subgoal 2, I'm going to apply permutation appcom, which swaps around the outer plus plus. So I do that in subgoal 2, and now this is what I have. And if I rewrite by the associativity of append, now I have utter on the front. So what theorem do I use? I don't know. Let's search about that. A plus plus b is a permutation of c plus plus d. That's how you write this search command. And it says if L is a permutation of L prime, then L cons tail is a permutation of L prime cons tail. That's not what I want. Here's another one, permutation app head. If tail is a permutation of tail prime, then L cons tail is a permutation of L cons tail prime. So that's what I want with utter for L. So I apply permutation app head, and then I finish off in that kind of way. Perm skip is useful, that if you have the same thing on the front, in this case F is on the front of both lists, I can just pick it off. Perm skip picks off the F on the front of both lists and leaves this subgoal, and perm skip picks off the L and leaves that subgoal, and perm swap does that. All right, that was mildly painful. It's actually more painful than anything you will have to prove when you prove sorting algorithms, because the sorting algorithms permute 2 or 3 things at once, not 9 things at once. And so you'll use these theorems, but it won't nearly be that hard. So in perm.v, there are some little exercises which are worth doing to get used to permutations. But I really want to move on to sorting. We could do insertion sort. So suppose you want to sort small to medium length lists. Insertion sort works perfectly well. Yes, it's a quadratic time algorithm, but it has good constant factors and quadratic on smallish lists is not so bad. Insertion sort is a sort of useful algorithm in many circumstances. Selection sort is rarely so useful. It's also a quadratic time sorting algorithm, but its constant factors are higher. It's harder to implement. It's harder to reason about. It's a little slower, right? There's rarely a reason to use selection sort. So, which one do you want to do for homework? Raise your hand if you want to do insertion sort and you want me to show you selection sort in the lecture. You should be raising your hand now. Otherwise, you'll have to do the hard and useless one. Okay. So here's selection sort.
What's the file?
It's selection.v in VFA. So, let's see. Yeah.
After we've proven that one of those sorting algorithms are correct, can't we just write an LTAC function that uses it to check if two permutations are the same, like just sorting them and checking if they're equal? Like having some sort of...
Yes, right. So if you want to, if your goal is to prove things about permutations like flutterby and butterfly, you should sort them and check if they're equal.
And then instead of proving the different sorting algorithms are, and whenever you want to prove that the sorting algorithm is correct, you want to prove stuff about permutations. So why not just have an LTAC function sort them, check if they're equal, and then apply it?
Because you're implicitly using the correctness of the sorting algorithm, which is the thing.
No, but it's an LTAC. But it's an LTAC, right? Like, no, you prove that one algorithm is correct. And
Well, okay. Maybe what you're saying is, could one write an LTAC program to automatically do proofs of the kind that I just showed? And the answer is probably yes, you could. But it's unnecessary because the proofs you have to do about permutations for these sorting algorithms are for much smaller lemmas with only 2 or 3 things in them. So it's not worth the trouble, I think. Probably. Here's a select function. So select XL is going to pick the smallest element in the list x cons L and remove it and give you the rest of the list separately. And it has these 2 arguments in this way because select doesn't actually work. This is not the sorting algorithm. This is just one pass of it. And it doesn't make sense to do it on the empty list, right? So we're going to give it x and L, which you could think of as x cons L, and it should return back an element and a remainder, right? That's the smallest element, and then the remainder of the list x cons L. So here's how it works. If the list L is empty, then it's easy. The smallest element of x cons L is x, and the remainder is nil. And if L is head cons tail, then if x is less than head, then grab the smallest, well, if x is less than head, then still we have to look at all the tail. We know that h is not the smallest element, but it still could be x or anything in the tail. So we have to select the smallest element out of the tail. That's j. This gives us the rest of x and t. That's L prime. And then we cons h back onto L prime. And if x is greater than head, then x is not the smallest element, but maybe h is, or maybe it's in t. So we select ht. That gives us a smallest element j, and the rest of the list that we cons x back onto. That's just functional programming. And now we can implement selection sort as follows. If L is I cons R, then we should select the smallest element in I cons R, call that element j, and the rest of the elements R prime, and then cons j onto the front of the recursive call to cell sort on R prime. And if L is nil, we return nil. So that's the algorithm, but Calc is not happy. Recursive definition of cell sort is ill-formed. Recursive call to cell sort has principal argument equal to R prime instead of R. So What's it complaining about? This is a perfectly well-founded definition of sorting. It does not infinite loop or anything. But when you make a fixed point in Coq, you must do your recursive calls on things that are substructures of the original structure. And I mean immediate substructures that, Coq can tell from your pattern matching and nothing else are substructures.
When I try to do that in 8.6, it just accepts it.
This is 8.6. I'm sorry. Something is weird. Maybe it's a comment, and it accepts it because it's a comment. It accepts it this way, because that was a comment. All right. So we can't use fixed point in this way. We have two choices. We can use some other mechanism in Coq, such as function or program fixed point, that doesn't impose this restriction. And those are built on fixed point. But let's try and use the most primitive thing. Let's do this homework with the fewest possible features of Coq. So we'll use fuel. So you've seen fuel already twice, at least, in the last 2 weeks. Let's do selection sort with L and N. Structurally recursive on N. And what do? It's the same as before, except that if we run out of fuel, we return nil. And the recursion is on R prime, which is what we want it to be on, and N prime, which is the one less fuel. So it's just the same function. It's a fixed point, nice and simple, but with fuel. And what happens if we run this with not enough fuel? So this is the example called out of gas. Do a selection sort with not enough fuel on 31415. Let's show this. Well, it's simplified down to 113, which is not a permutation of 31415, although it is in increasing order. Okay, so, and to prove that it's not, well, okay, so remember here's what I got when I did the simple. That's the thing I'm trying to prove, that 113 is not equal to 11345, and by intro and inversion, it's proved. What if we have too much fuel? So cell sort 31415 with fuel 10, which is way too much. So we get the right answer. So too much fuel is fine. Not enough fuel is no good. How much fuel do we really need? Well, the length of the list. So selection sort on L is defined as cell sort L with fuel length of L. And now we can sort 31415926535 equals 11233, etc. So we proof unfold selection sort. So we're doing cell sort on that list with fuel length of that list. If we simplify, we see that it appears to sort. Okay, now a sorting algorithm gives you a permutation of the input that is sorted. So we've defined permutation. Now we have to define what it means for a list to be sorted. Well, the empty list is sorted, the singleton list is sorted, and for all I, j, and l, if I is less than or equal to j and j cons l is sorted, then I cons j cons l is sorted. We need 3 cases. Yuck. Doesn't seem like we should need 3 cases. Seems to me in the end we need 3 cases. I don't have a way better way of doing it than these 3 cases. Okay, so here's definition. Is a sorting algorithm, takes a function whose type is list_nat arrow list_nat, and makes this claim about the function that for all lists AL, f of AL is a permutation of AL, and f of AL is sorted. So that's our specification of what's a sorting algorithm. And here's our proof. Okay, first we're going to prove that select, which is just the one pass of selection sort, is a permutation. So select, if we do select XL and get back YR, then X cons L permutes into Y cons R. That's the theorem, right, about select. And how do we prove it? Well, here's how we prove it. We're going to do induction on the length of L. Makes sense. Induction on L. But we had better move X below the line. If we were to do induction on L right here, it wouldn't work. Because as we move down the list, which element appears in the X position may change. So we need to generalize this by moving X below the line before doing the induction. You've seen that already a couple of times in software foundations. This is one of the most fundamental things you need to know about doing induction proofs in Coq. You don't need to know it about doing induction proofs in like LaTeX or logic, because inductions in LaTeX almost always work, right? Okay, but when you're doing them in machine-checked logics where it actually has to be right, then you have to properly generalize your induction hypothesis. Okay, so now we can do induction L, and I'll put a semicolon afterwards. In both cases, do intros and simplify everything. So now we have two cases. But this is an exercise. Oh, but I was supposed to do the exercise. Okay, so I'll say constructor. There must be some constructor of the permutation inductive data type that works here. And so yes, it picks off the X at the front. And now there must be some constructor, I forget its name, about permutations that does that. That solved that case. Okay, in the other case, oh, look at all this stuff. How are we going to do that? Now, when you do insertion sort, you'll be in similar situations. What do? There's an if. So we're going to do B destruct on X less than or equal question mark A. And now we have two cases. And above the line in the first case, we have this very handy H, which says X is less than or equal to A. Now what do? We have a let. What do we do with this let? And it's a let. It's another let. So the inner let, at least, says let J L prime colon equals select XL. What do you do in Coq when you have to prove something about that? We want to pick apart the select. Select XL has type that's a pair of a nat and a list of nats. So we're going to say destruct select XL EQN question mark. So what did that do? Above the line, you can see the equation. It's broken select XL into two pieces, N and L naught. Now, that's the equation. And it's replaced select XL below the line with N L naught. And then the rest of the things just simplified away. Okay? So when you have a let, and you want to be able to analyze it in a Coq proof, this is, and if the let is for one of these tuples on the left-hand side, this is the way you tend to approach it, with a destruct and an equation. Okay, so now what? Well, the induction hypothesis looks useful. IHL up there, it says if you had a select XL for some X, then you would learn things about it. So how do we make use of that? The X in the induction hypothesis is not necessarily the same X as we have down here. We will specialize the induction hypothesis with our X, right? So that turns it from a for all into just a statement. And then we can rewrite by HEQP in IHL. And now we've learned this. X cons L is a permutation of N cons L naught. All right. And so from IHL above the line, let's clear out the stuff that's not relevant. This is the kind of thing that we were proving in the permutations file. And, you know, in about 3 steps, you can do this. You have to swap the X and A. I don't think this will work. Yeah, it does work. Yeah, that's good. Constructor. Now what? This probably doesn't work. No, apply. One weird thing about the calc permutation library is the inconsistency of naming. All right, so there's some theorem that I'm running out of time, so I won't prove for you. But then we're done with this proof. And we have to prove that selection sort is a permutation. So that's just another induction. And then the last one is not even an induction because we just unfold selection sort. And it's a proof about cell sort. So I'd hoped to get further than this by 15 minutes ago, but I didn't. What I didn't show you is how selection sort is sorted. All right, I'll stop here. The homework is not to work on selection sort. So you should skip right to sort.v and prove things about insertion sort. Insertion sort, look at insertion sort. Here it is, just these lines. And there's no fuel. There's just ordinary fixed points. It's fewer lines of code than selection sort. It's natural to think about. It works well. And it's not too hard to prove things about. So your homework really is to prove the exercises in sort.v, although you can omit the optional exercises like multisets and so on. Okay, that's it for today.